Hello math fans, continuing the series on cutting up pancakes. Again, I'm working through a project and giving kind of the history of this project from, I actually think it was, I may have misspoken last video, but 2010, 2011, 2012, when I had these honor students. Watch my previous video where I talk about it. In this video, I'm just going to talk about cutting up a 2D pancake. You might say, why 2D? Well, 3D is going to be the next video. This actually stems from me cutting up Egos for my kids. So I'm just going to talk about cutting this up. I do want to just mention, as I didn't in the last video, I just went and posted these on my materials website. If you do a Google search for Andy Lovelace, of all the Andy Lovelaces in the world, I have the biggest website. Lots of review materials. Some of this I used to not have up, but I'm adding it now. So we're basically working through this old worksheet of mine from a long time ago, this project. So this is what we did in the first part. My 3-year-old wanted me to cut it up into 9 pieces, blah, blah, blah. So then I talk about, I want you to find the general formula for how to cut up a sphere into thirds. Now that problem actually has more of a history. There's even puzzle books on if you have a circular gas tank for on the side of a truck, where would you mark it so you would know where a quarter is and a half and things like that. So this will be an opportunity for me to do a little bit of calculus. So this is more for those of you that aren't calculus people. I don't know how you found me, but this is going to be more of a calculus discussion. I'll end it with checking against my solution from years ago, but it's mostly a chance for us to talk about trig substitution. So let's impose a coordinate system. And I'm going to impose a coordinate system where the center of this Ego is right in the middle. I don't know why I used that color. That was stupid. And let's cut this up into thirds. So we're going to call this line, and that might not be reasonable what I just did there, but let's call this x equals a. Let's say this is the x-axis and this is the y-axis. And let's call this x equals minus a. It does look like I did a poor job of doing those because I wanted all 3 of these things to have the same area. Probably shouldn't use green for food, but I certainly drew it poorly because the middle one looks like it's way bigger. So imagine I push this one this way a little bit, maybe push this one over. But we want all 3 of those to have the same area. So this is a chance for us to use integral calculus. Now, in the order I want to do this in, but let's just talk. So let's take a point on the edge of this circle. We're going to say the radius is r. And we're going to say this is a point xy on the edge of a circle. So I'm assuming people know the equation for a circle. If you don't, it's where the distance from this point to this point is always r. Using Pythagorean theorem or the distance formula, you get this. So there's our starting point. And the challenge in this problem is we're going to treat r like it's a number. If that part bugs you, replace r with 2 or 1 or 5 and do it with a number and then see if you can follow along. But it's better to do it with an r because I can solve a whole bunch of problems at once. Okay, so there's a few ways to set this up. I'm going to do it all in terms of x. So if you're one of my students, you'll know that the very first thing I do on area questions is I either label x or y. So let's label this x. I know I have a bunch of stuff on there now, but you can handle it. And so the distance to the top and the distance to the bottom, I would like to label. Now, the top is going to be whatever you get when you solve for y. So you're going to get y squared is r squared minus x squared. And I talk a lot about the importance of labeling. There's 2 possibilities. This cannot be simplified. That's called the sophomore's dream. If you're my students, you've heard that many times. That you'll see students do this over and over and over and over again. And I got to be careful because my head always appears in the corner of these videos. But you'll see students write this as 3 plus 4. And I encourage you to convince yourself that those are not the same because this is the square root of 25, which is not 7. Square roots do not distribute. It's called the sophomore's dream because so many sophomores and freshmen have gotten that wrong for so many years. I didn't make up the term sophomore stream. It's been around for a long time. Okay, this right here, I've erased my line. And I'll probably redraw this in a second because I've successfully made it look just terrible. But this height is the square root of r squared minus x squared. And this, the distance from here to here, well, not distance, the value is negative square root of r squared minus x squared. So for a given radius and a given x value, those are the heights. Okay, so those of you that have taken this calculus course, you know that we have this tool, this integral tool, which finds the area. If you can figure out the top function and the bottom function. Again, I'm being a little casual here. In class, we did this more formally, and you can figure out where to start and end. Now, back when students did this, they did it in various ways. Some people did it from a to r. This is x equals a, this is x equals r. So one way to do it is say a to r, and the top is the square root of r squared minus x squared. Let's just talk setup for a second, and then we'll do the computation. Minus the negative. It's a fairly classical type of example, but maybe for someone that's just struggling with trig sub, this could give you some insight. This is a plus or minus, so we get 2. We get 2 times the integral from a to r of the square root of r squared minus x squared dx. That's what this is. This integral actually does just represent this top half, which a lot of my students did when they did this problem. Some of my students decided to focus on this piece. And so they did 4 times that to get the area. They did 4 times the integral from 0 to a of the square root of x squared. So some students set it up this way. Some students set it up this way. You can see the advantages of setting up this way is that one of your bounds is 0. Okay. I'm 4 because this would just be one of these. You could also set up this one, but that has negatives. I don't want it. So anyways, we'll either do this, which represents, let's call this region 3. This is the area of region 3, if we can figure it out. And this is the area of region 2. Area of region 2. So, and then region 1 is the same, but I'm not going to write it up. It would be the integral from negative r to negative a. Same thing. Okay, and I'll end this video with a little discussion of other ways to do this. I know someone watching might say, I can do that without trig sub, and you're absolutely right. But trig sub gives us a way forward if we can't think of anything else. Okay, so right now, let's pick one of these and talk about a few things. Our goal, before we start embarking on this problem, is to make it this one or this one, doesn't matter. You could set them equal to each other. Those of you that have done area questions before know that that's not always the cleanest way. Usually the cleanest way is to find the entire area first. So the entire area is going to be pi r squared. And we want this to be a third of it. So the goal of this question, and in general, in all my math classes, I talk about what are we given and what do we want. So we're given this information, and what we want to do with it is we want this or this to be a third of that. So we would like 4 times the integral from 0 to a of the square root of r squared minus x squared dx to be a third of the total area. And now we're ready to embark. And I think students get the wrong impression of calculus. The calculus part is like arithmetic. Once I get here, I'm like, all right, I'm in business. I can compute this. But having taken calculus, you know that this is a doable problem. I feel like that's part of what you're learning is which things can we solve. Okay, before I have my notes here, but we'll come back to those later. So now let's actually integrate away. And let's focus on just this piece. I'm going to go through that fairly quickly. That's more for my calculus students. But we have this very clever method that uses the fact that it's incredible. It's an impressive method. Uses the fact that these are the same. That's a unit circle fact. And somebody had this clever idea to replace x. So right now we're going to work on this piece. replace x with r sine of theta, which really feels weird. It really feels strange when you first see this to say, I'm going to replace x with something worse. So I always tell students that's really a surprising maneuver, but then if you can see a step ahead, and the last couple of years I've been playing chess, and I feel like this is one of these situations where someone can see too many steps ahead, and I'm in trouble, I'm going to lose. I can't see enough steps ahead. Okay, so here we go. This is what they saw would happen, that this would be cosine squared. Why is that helpful? Well, it gives us a way to deal with the sophomore's dream problem, which is we can't distribute this, but we can simplify this, provided that cosine is positive, but over the domain of values we're dealing with, cosine would be positive if we chose appropriately. So there's subtleties, which I'm not going to talk about now. I'm just going to say this. So what happens? This will become, and I could leave the 4 or move it to the other side. Let's move the 4 to the other side. Let's just be careful when we do that. So this is going to be 12, and this is our goal. That's our goal. Okay. So let's come back. And we can either change the bounds or not. 0 is not so bad to change. When we plug in a 0, we get 0. That's in the principal domain when sine is 0. So this is going to be 0. But the other thing is not quite so nice. Let's call it a star. An A star, maybe A star is a bad name. Let's call it theta star. Theta star would be when A is equal to R sine of theta. I don't know why I inappropriately laugh at everything, but this should not be a dry thing. Math allows us to solve problems. It shouldn't be a dry, boring. You say, hold on, I fell asleep already. What did you say? Okay, so this is what I'm calling theta star. Okay, so here we go. The whole point of trig substitution is we got rid of the square root. We completed the sophomore's dream in the best way we could. Yay! But you got to change everything else. Dx is r cosine of theta d theta. So this is r cosine of theta d theta. And we can factor out an r squared. And we'll come back to this at the end. 0 to what I'm calling theta star of cosine squared. That completes the basic idea of trig substitution. Was this clever idea. Now the bad part about trig substitution is it does not solve the problem. Trig substitution just gives you a new problem, which is a trig problem. Now trig problems, we have a very clear procedure for how to do them all, but you have to know the procedure. So briefly, if you don't know the procedure, that's something you should be learning in your classes. I talk about this in class. We go through the examples. Basically, these are the examples. And when I teach it, I basically say there's only 2, even though it looks like there's 1, 2, 3, 4, 5, 6 examples. I think there's only 2. There's the examples where you have an odd power somewhere with sine and cosine, and it's just a clever use of our identities. And there's an example where you have a tangent or a secant. And then there's one special case, which is when you have even powers of sine and cosine. So I hand this out in class, and this contains the answer to, in one page, yes, it's kind of a bunch of stuff to learn, but in one page has the answer to everything. Every trig problem we can integrate. Okay? So there's stuff to learn there. And that's what's hard about trig substitution is it builds on this other piece. And then I have this sheet where the trig identity part I need to remove, but this is the whole idea of trig sub. So hope that helps somebody. If you do find that helpful, let me know. You know, I get paid less than a middle school math teacher. So if you can find a way to slip me a few bucks, I would take it. Oh, I shouldn't say that. All right, here we go. Back to the problem. So this is one that we can do because we can use a half angle identity. So it's the integral from 0 to theta star. I get paid less than a middle school math teacher that has the same amount of experience, I should say. Same number of years of teaching. UW just doesn't pay teaching professors very much. Okay, so there we go. This should be a plus. I better not make a mistake while I'm complaining about my pay. Okay, so then we have r squared over 2. And then let's integrate. This is theta plus 1/2 sine of 2 theta evaluated from 0 to whatever in the world this theta star is. Now, because I'm doing a video on trig substitution, I wanted to mention that there is a way, and I'm going to have some other stuff to talk about. I keep running out of space. There is a way to return to your original variable. And this is always another challenge students face. It's an incredibly valuable little skill. It involves, okay, there's a problem with trig sub, which is that it's not as natural to return to the variable because our old variable is here and our new variable is kind of stuck inside of a function, which is different than most substitutions. That's a different discussion. So here is the one main case where you need one other half-angle identity. So you need this half-angle identity to integrate. You need this other half-angle identity to clean this up. And it turns out this collectively is the same as cosine of theta, sine of theta. And without that, it would be hard to return. Now, sine of theta, we can figure out. Sine of theta, based off of our substitution, is x over r. That's this right here. I just moved it to the other side. So this is going to be x over r. Cosine of theta, and students don't like this the first time they see it, is you can quickly get from one trig function to any other trig function. Sorry, that color's terrible. By drawing what this means, by doing the SOHCAHTOA. Opposite over hypotenuse. So this is x over r, and then solving for the other side, which is the square root of r squared. This is all stuff, if you're watching this video and you've never seen these before, you need to take a course in calculus. There's a lot of little things happening here, but this at least justifies a little bit of why we care about that. And then you can say cosine is adjacent over hypotenuse. If you do this, then it allows you to return to your original variable, meaning you're going to have an r squared over 2 out here. Theta, there's nothing better you can do than just say inverse sine of x over r. And this is a big, hefty looking integral. And now we can return to the original variables, which were 0 and a. Whew! Not that bad. You can do that. Anyways, then you plug in an a everywhere, and you get r squared over 2 arc sine of a over r plus, there's going to be an r squared on the bottom, but it's, we should expand, but I'll do that in the next step. And then it's going to be the square root of r squared minus a squared times a. It's good to put a little hook on your square roots. And so nothing escapes. Now, if you plug in a 0, you get 0 here, and you get 0 here. So there we go. There's our formula. If we distribute the r squared, we have 1/2 r squared arc sine a over r plus 1/2 a times the square root of r squared minus a squared. And let me just peek at my solution. We'll come back. We'll check it in a second. Let's assume I'm doing all right. So at this point, we want that. This is this thing we've been, now we get lost. We're lost. Couldn't you be more organized? Absolutely. But that would require time. So I want this to be equal to 1/12 of pi r squared. Can we clean that up at all? So multiply everything by 2, you get r squared arc sine of a over r. And you really have a lot of scary looking things in there. R squared minus a squared equals pi over 6 r squared. Okay. So what I had students do at that point, I said, this is going to be hard to solve precisely. without the help of a computer, which is why we often don't ask questions like this, because in the end I can't ask it on a test because you can't solve that resulting piece. Okay, so what, and let me check what I got here. Let's see how we did. Oh, I did it from 8R. I don't know if that's any better or worse. But in the end, I got this equation. And I divided everything by... Ooh, I did some clever stuff there at the end. Let's look at it. So I took this and I divided everything by r squared. Good job, me. It is funny to look at your work 12 years later and be like, oh, I used to be smarter. R squared minus a squared over r squared equals pi over 6. And then I simplified this. I told students to rewrite this as t. And then I had them move this to the inside by writing a fourth power and a square root. Let's see if I can show you that real quick. A squared. I hope I've gotten wiser, but I think at the same time I've gotten dumber in some ways. R to the fourth. Oh no, I left one. I left one R out here. See, I have gotten dumber. And I put only one R inside, so this is an R squared. Aha! Hee. And this is actually t squared. This is 1. So it was this clever maneuver to get rid of the R and the A. A over R is actually like a percentage. But I was trying to show that it doesn't matter what A and R are if we're just trying to solve this. So I was just trying to show that we're basically solving. So the good news is I got the same equation, and then I told students to put that into a solver. So let's do that now. At the time, I think I had to explain to students how to use a solver. I imagine students know how to do this now because everyone's been cheating on their homework. So let's go solve arc sine of t minus t times the square root of, and it just depends on what sort of calculator you're using. And we're about to find out. I didn't test this out ahead of time. But I imagine plus look at that answer. Oh, there we go. 0.264932. So about 26% of the way out. Okay, so that's what we get. This 26, so t, I get t is 26, sorry, t is 0.264932. So what's the conclusion after all this huge waste of time is when you're making your pancake, let's grab the pancake. Let's put it down here. Spherical pancakes are the next part. You have to, your A over R. So A is going to be 0.264932 times whatever your radius is. So you need to go to whatever the middle is. You need to go 26% of the way out. If this is 100%, you need to go 26%, whatever that is. That's where you make your cut. It's about a fourth of the way out. And it's going to be from negative 0.26 to positive 0.26. So that means there's going to be a lot. It's pretty close to the middle, but it sort of makes sense because you have a lot of, because it's much wider there. And what we found in our further studies was that when you go to higher dimensions, you have to cut closer and closer to the center to get most of the volume or mass, which we'll follow up in my next video on that. In some ways, 2 dimensions is one of the hardest to deal with because the integration is the most involved, as you'll see. And I always try to say you need trig sub if you're going to integrate with things involving circles. Okay, so sorry for the mess here. But in the end, what do we have? Hope that was kind of interesting, allowing me to arrange. I'm sure in the future I'll need to clean up some of these videos, but I just wanted to get it started. If this sort of thing interests you, I'll clean it up and keep making more. Let me know in the chat. My goal is to give these ideas of why these things are of interest, which I don't usually get to take time to do in class. I often am just having to, give you the content. So here we go. Summarizing, we can cut up a pancake into thirds. We need to go about 26.5% of the way out from the origin towards the sides, and do that on both sides. All right, thank you.